Quick reminder that you have the deadline for coursework 1 is this coming Sunday at midnight. So you also had, I think, the second class or labs with Yang or Longfei this week. Hope that was helpful. By now, I think you should be in good state to actually, work on coursework 1. You'll see coursework 1 is not very difficult, but it's quite important that you're all familiar with this kind of problems and techniques. Good. So today, let's continue our analysis of MIMO channels, and we were talking about last week. We were talking about the capacity of MIMO channels, which we started playing with. And so what we're going to do today is that we're going to continue that, and we're going to hopefully finish that analysis. So we're going to continue with deterministic MIMO channels, and then look at fast fading and slow fading. And we will try to understand what is the optimal way of transmitting over MIMO channels. How should I actually pre-code information? How should I actually allocate the power across those different streams, and so on. Good. So last week we finished with this here, where I explained very briefly that essentially we're looking at mutual information. Your rate at which you can transmit reliably is actually captured through this mutual information. And this is the mutual information between the input and the output that is obtained when you have Gaussian inputs. So here we assume we have circularly symmetric complex Gaussian inputs. So your Q here is now the covariance matrix of those inputs. So this is called the input covariance matrix. And so the capacity is the maximum of the mutual information. For those who actually take information theory, you will see this in much more detail. The capacity is the maximum of the mutual information when you look at this over all possible inputs, right? And so to maximize, when you have Gaussian channels, to maximize the mutual information, you need to have Gaussian inputs. But here, because you have MIMO, you have also additional things to optimize, which is your input covariance matrix, your Q. Right. So the capacity for a given channel matrix H is given by the maximum of that quantity when you optimize over Q, and Q is such that the eigenvalues are positive and the trace of Q is bounded here equal to 1. That means actually you bound the average power of your input signals, and you cap it to 1, so that whatever number of transmit antennas, you always have a fixed average transmit power. That's what it means. Good. So this is actually a more general expression than what we had earlier on for the SIMO or MISO or SISO, right? If you and this is what I explained last week, you can always particularize this to one antenna at the transmitter or the receiver, and you will end up with the expression that we had we saw earlier on. Good. So the question we have now is, how do we find this Q? So what is this Q? And so the first thing we have to remind ourselves is what we did earlier on. A few last lecture, we had this thing here. Remember what we were trying to do? We had this matrix H, and we were pre-coding on the right side using the right singular vector. So we had H was we were saying H is UH, this BH remission, right? So we're doing a singular value decomposition of H, and then what we were doing is transmitting on the right side along VH, and on the left side we were combining around UH. So by doing that, we have this magic that if you combine using UH remission and you transmit using VH, then that means that you have UH sigma H VH remission. On the right side you put a VH, on the left side you you do this. So this is your receive combiner. This is your transmit precoding, if you like. And so those two will cancel each other because those are unitary matrix, and what you end up with is just this, right? So you're going to have now transmit multiple streams at the transmitter, and because of your precoding and combining, all those streams are completely decoupled with each other. This is what you see here. All those streams in this vector C now, imagine you have two streams, C1 and C2. They're both traveling through two non-interfering paths. And so that will create your multiple parallel data pipes and your multiplexing gain or spatial multiplexing gains that you have in MIMO, right? So to do that, you need to know H of the transmitter and the receiver, and so you can really transmit along the right singular vector and combine along the left singular vector, right? So this is what we did last week. Now, if you do that, right, it means actually what you transmit essentially is VH multiplied by C. So now your covariance matrix of the input, this is your input, this is your transmit signal, and you have to compute the covariance matrix of this. C, we assume, is always Gaussian distributed, circularly symmetric complex Gaussian. So if you calculate the covariance matrix of this, right, you're going to have expectation of VH C Hermitian VH, right? And this is going to be VH multiplied by expectation of CH VH Hermitian. Now you transmit independent streams. So because they're independent, this quantity here will be diagonal, and the diagonal will tell you how much power you allocate to each of those streams, right? So you're going to have input covariance matrix, which relates to the right singular vector of this matrix H. And you're going to have the diagonal entries of this quantity here will tell you how much power you actually allocate to each of those streams, or how much power you allocate to each of those data pipes. Okay, and so this is what we see here. Our input covariance matrix Q is this with the C prime, right? So our C prime here is this, right? C prime is our precoded streams, our streams that has been precoded, right? And so what we have is here is exactly what I expressed already before. We have our input covariance matrix Q will be a VH and VH Hermitian, and then we have here, this is actually this quantity here coming from this expectation of this, because they're all independent from each other. I transmit independent streams, right? They're circularly symmetric complex Gaussian random variables. So what I'm going to have is just this going to be a diagonal matrix, and the diagonal entries are just the power that they allocate to each of those streams, right? Essentially, if you like, this is the diagonal entries will be simply the variance of each of those elements there, right? Of the entries of this vector C. And so this is what we have here, right? SI is now the power that you allocate to each of those streams. So if I have if I take a photo of this, draw. Right, so I have, let's say, two transmit antennas and two receive antennas. I have a matrix H. What I do here, I do VH at the transmitter. What I do at the receiver is UH Hermitian, and you remember H is UH sigma H VH Hermitian, right? So that's the processing I do, and now I transmit here two streams. I have a stream C1 and a stream C2. Right? Those are two. I assume they're Gaussian distributed in order to achieve the capacity, and I allocate a certain power to C1 that is equal to S1. And I allocate a certain power to C2 that is given by C2, right? So S1 here will be the expectation of C1 square, and S2 will be here the expectation of C2 square by 1. Okay, so it's the power that I allocate to them. Right, good. So what we end up with is now we have an input covariance matrix that is equal to that. So if you do that, and you take this and you plug this into here, what do we have? We have, let's say Q is VH, the diagonal matrix, VH Hermitian, and we have this expression, determinant, log of the determinant. So log 2 determinant INR plus H Q H Hermitian. Now here you have to note, I put a row here, right? So this is always my long-term SNR, right? So here, to be strictly accurate, this is, I could define S1 as the power of each streams, or I could say my total power will be something, and I look at S as the fraction of the total power that I allocate to each streams. So this is actually a different way of looking at this. They are all equivalent. So here in the notes you will see, because I write a row here, it means that actually I already effectively capture the transmit power that I have, and what I put in the diagonal entries of Q is just a fraction of the transmit power that I allocate to each streams, right? We'll see an example later on where I don't use the row per se, and I directly allocate the absolute power to each streams through this Q, right? So those are different writing you can find in the books, and you will see I will use both so that you're familiar with this. So here, if I write that the sum here, the sum of those elements is equal to 1, right? That's coming from the fact that the trace of Q is equal to 1, is because effectively I capture the SNR through this row. And so what I'm looking at is actually how a fraction of the transmit power is allocated to each of those streams, right? So I will get into this later on a bit more so that you understand exactly how to write this. Right, so let's plug this into this, right? So I had this row here, and now I have those diagonal entries. And so I have S1 plus S2 is now equal to 1. So I have the sum of the power to the first stream and the second stream that is normalized and equal to 1. So S1 is the fraction of the power allocated to the first stream, S2 is the fraction of the power allocated to the second stream. Right, so if I have this and I plug this here, and let me call this, so let me do this for the 2 antenna case, right, this example here, so we'll understand better. So I have 2 receive antennas. And so here I have this quantity is S1 and S2. Right, now if I do that, what do I have? I have here, I can write this equivalently. This is log 2 det I2 plus rho Q H Hermitian H, right? So if I have that, what is H Hermitian H? Let me take another color. H Hermitian H is UH sigma H VH, and here I have UH Hermitian sigma H VH, right? So this is identity. So here what I have here is essentially a VH, and then I call this lambda, and then VH Hermitian, right? What is lambda here is lambda H is lambda H is sigma H squared, right? So this sigma H is sigma 1, sigma 2. I have 2 singular values. Lambda H would be lambda 1, lambda 2, with lambda I is equal to sigma I squared. Okay, so square the singular values. Right, now I plug this into this equation here, and so I have log goodness. log2 that I2 plus rho, what is my rho, is VH multiplied by S1, S2, VH remission. And now I'm multiply here by this. I have VH, lambda H, VH remission. Right. So what you see here, this one will cancel this one, is a unitary matrix, right? And I can write this again, log2 that I2 plus rho, and I take the VH and I bring it the other side, multiply by lambda H, and then I have VH remission multiplied by VH, right? Here again, this is identity matrix, right? Because it's unitary. Right, so now I have log2 that I2 plus rho S1, S2 multiplied by lambda H is lambda 1 and lambda 2. Right. So this quantity here is essentially 1 plus rho S1 lambda 1, 1 plus rho S2 lambda 2. That zeros there. And then doing a determinant, the log2. What is the determinant of a diagonal matrix? It's the products of the diagonal elements, right? So I have log2, 1 plus rho S1 lambda 1, multiplied by 1 plus rho S2 lambda 2. And so this is equal to log2 1 plus rho S1 lambda 1 plus log2 1 plus rho S2 lambda 2. Okay, so that's my rate now. That's my rate. And what is the capacity? The capacity will be, so I just did the whole development here for 2 by 2, but in general, you're going to end up with this relationship here. You go from K1 to N, where N is the number of actually the minimum between the number of transmit and the number of receive antennas. So that's the maximum number of non-zero eigenvalues you can have in this, or singular value that you can have in H. And you have the log of 1 plus rho sk lambda k. So exactly the same expression as what I had here, but here I just have 2 of them because I have a 2 by 2 matrix. So our N is equal to 2 in this equation here. My N here is now equal to 2 in that example. Okay. Now what I have to find is the maximum among all S that maximize this. The maximum, the S that maximize this, that's going to be my capacity. So I have here the capacity will be the maximum over S1 and S2, right? With S1 plus S2 equal to 1 of log 2 1 plus rho S1 lambda 1 plus log 2 1 plus rho S2 lambda 2. That's what I have to find. Okay, so for those who are familiar with optimization, this can be solved using convex optimization. For those who are familiar with Lagrangian optimization, you can write the Lagrangian of this problem and find out the value of S1 and S2 that maximize this, right? So if you take, if you're not familiar with Lagrangian, you can still go into the book, right? You go to the MIMO book and you will find the derivation of this, how we can obtain that. Right, so what is the solution of this optimization problem is the following, is given by this. If you have the power allocation S, the optimal one, so that's why I highlight this with stars, that maximize this quantity, but subject to a power constraint that is equal to that, is given by what is called the Waterfilling solution and given by this relationship here. So let me explain you what that means. Let's first imagine that I have here, I have rho. If rho is small, My long-term SNR is very small. So that means actually maybe I have a fixed noise power, but my transmit power is very, very small. So what that means is rho is small, rho S1 lambda 1 will be small, and rho S2 lambda 2 will be small as well. Right. Now, if you have a log 2, 1 plus x with x small, this is roughly x log 2e. Right. So it's linear with x. That's what it means. Right. So roughly rho is small. What I have is C will be a max over S1 and S2. S1 plus S2 is equal to 1 of rho S1 lambda 1 plus rho S2 lambda 2. Right, so here imagine what you see. I'll write this slightly differently. I have just a rho S1 lambda 1 plus S2 lambda 2. And I have to maximize that, and I'm subject to a constraint that S1 plus S2 is equal to 1. Right. Any idea how I should allocate S1 and S2? So I need to find S1 and S2 and to maximize this, but subject to the sum equal to 1. What would you do? Any idea? Who wants to try? Anyone? Imagine lambda 1 is larger than lambda 2. Imagine lambda 1 is larger than lambda 2. Right. So that means that if lambda 1 is larger than lambda 2, right? Okay, I have someone. Teacher, yes, please.
Can we replace S2 by 1 minus S1 and then replace the S2 in the formula and take the
You could do that. That's right. You could do that in this example here. You could do that. But if you have more than 2, then it's a bit more complicated because you still have many variables to optimize, right? You see? Yeah. So here, what I want you to try to have a sense of what happens here in the low SNR. So imagine lambda 1 is larger than lambda 2. So if I put a bit more power to S1 and S2, then this term will increase more quickly because the weight here is larger than there, right? If lambda 1 is 10 and lambda 2 is 0.1, well, if I add a bit to, is it better to add a bit to S1 or a bit to S2? You would say it's better to add to S1 because simply the weight is much higher, right? If I have 10, anything I add here to S1 will be multiplied by 10, while here anything I add to S2 will be multiplied by just, let's say, 0.1, right? So you see, the solution to this is such that you actually allocate all your power to the strongest eigenvalue. So if lambda 1 is larger than lambda 2, what you do is that you take S1 equal to 1. You put all your power to the dominant one, to S1, right? So what that means is that if I have my MIMO channels and I have 2 transmit antennas and 2 receive antennas, and I have decomposed into 2 paths, 2 virtual paths, right, where one has a strength lambda 1 and one has a strength lambda 2, and I know I have a low SNR, so my rho is very low. Well, to maximize the rate, what I should do, I should not allocate any power to the second stream and allocate all the power to the first stream. So what I'm end up doing is dominant eigenmode transmission. If I have very low SNR, the optimal power allocation here is to transmit everything through the dominant data pipes, the one with the strongest eigenvalue. Right. In that case, I transmit only one stream, and I allocate all the power to that stream. And which direction I choose is the direction of the strongest eigenvalue of the channel. Right. This is what happens at low SNR. Now, if your SNR increases, right? If your SNR increases, then you don't have this relationship anymore. the logarithm function is maybe linear at first, and then it becomes logarithmic. You know, it flattens, right? So imagine that now your rho increases. If your rho increase, at some point your return on investment is not that great, because if you go from here to there, right, you only increase from here, from this level to that level. It's not linear anymore, so you don't gain so much, right? So if your rho increase, what happens is that now you realize actually you start allocating power to the second eigenmode. So you will start allocating power only to the first eigenmode when your SNI is small. As your SNI increases, then you will start allocating power to the second mode, the one that is weaker. And the reason for this is because you have a logarithmic function, right? But this is what happens if you solve the optimization problem. This is what you will see, and this is what is reflected in this expression here, in this equation here, right? So let me explain you that. So we have a mu here, which is called the water level, and is a constant that we have to find, and we have 1 over rho lambda k. So what that means is that I have a certain mu, and then what I allocate to the power to the mode k is the difference between that constant and this. So imagine if lambda k, you have a certain SNR, but if lambda k is very large, right, compared to some other lambda k, so for one of them, let's say lambda 1 is very large compared to the other ones, this term here will be very small, right? So the difference between mu and that term will be large. So in other words, if one of the lambda is larger, you're going to allocate more power to that mode, to that data pipes, right? So in general, you're going to have n data pipes. Each of them has a certain strength that is given by lambda k. And the larger lambda k, the larger you will allocate power to that mode. That's what it says. Okay, so mathematically and you have here a plus here that says that if this term is negative, you actually do not allocate any power, right? So the x plus means is essentially is the max between x and 0, right? So if your x is negative, you just put 0. So either you allocate a positive power, obviously, or you allocate 0 power. That's what it says. Right? So if I draw this, what you get is the following one here. You have a certain mu, right? And you have 1 over rho sigma k, right? And imagine I have lambda 1 is larger than lambda 2, is larger than lambda 3, and so on. And I have n of them, right? So 1 over rho lambda 1, it will be lower than 1 over rho lambda 2, and so on. And I have a certain mu, which is a constant here. And that difference here is essentially the power that I will allocate to each of those different modes. So I have n modes here. And what it says that actually will allocate power to only 3 of them, the 3 strongest one. I will allocate more power to the strongest one, lambda 1, a bit less power to the second strongest, and a bit less power to the third strongest. All the other ones, I will not allocate any power. Right. This is your water filling. And the way you can interpret this is that imagine you have a bowl here, and you pour in some water. You pour in some water. So you pour a bit of water, a bit more water, right? So mu is your water level, essentially, is the level of your water, right, that you pour into the bowl. And this here, if you like, is your 1 over rho lambda, right? So if you have if you have a higher water level, it means actually you will start flooding, you know, giving water to more eigenmodes, essentially. Okay, that's a little bit the interpretation, right? But the main thing that you need to understand here is the stronger an eigenmode, the stronger you actually allocate power. And so what this is here is a constant that you have to calculate based on this constraint. The sum of those s is equal to 1. Right. So let's do that. This is what is done here. So let's imagine that I have that's an algorithm here to calculate this power level, right? And at each step of this algorithm, you actually calculate this constant mu. And then once you have mu, you calculate sk. So what it says is the following one. Let's imagine you order those eigenvalues in decreasing order. So lambda 1 is larger than lambda 2 and so on. Right? Now at iteration 1, you calculate the water level mu. So what is our mu? Our s, sorry. I'm taking the expression that we had before. I had s, k, is a mu minus 1 rho lambda k. Right, plus. And I know that the sum of those sk has to be equal to 1. Right. So let's imagine that I'm iteration 1. Iteration 1, I is equal to 1. And at I equal to 1, I assume that all those quantities are positive. So I'm writing s of k, and I'm assuming all those quantities are positive. This is the sum of mu 1 minus rho lambda k. And this has to be equal to 1. So that's going to be, and I have k equal from 1 to n. So I have n mu minus sum of 1 over rho lambda k. And this has to be equal to 1 to satisfy this constraint. So that means that mu has to be equal to 1 plus the sum k from 1 to n, 1 over rho lambda k. And I have 1 over n here. Okay, so this is the expression that we have here when n is equal to 1. When n is equal to 1, you see that term here disappears and that term here will disappear. Right? So now I have my mu at iteration 1, and now I can calculate sk will be mu, let me write mu 1, will be mu 1 minus 1 over rho lambda k. Okay, now what you do is that if this quantity is negative, you set it to 0. If this quantity is positive, you keep it, right? If you have one of them is negative, right, what you will do, you will go to iteration 2, where if one of them is negative, you set it to 0, and you go to iteration 2, where you have, once you have removed that stream to which you have allocated a 0 power. So this is what you do here. At iteration 1, you find mu 1. You calculate your power at iteration 1. If one of them is 0, is negative, you set it to 0. And then you go back here and you go to iteration 2. And so in iteration 2, you will only take n minus 1 modes, the one that are potentially non-zero, right? And you will recalculate your mu. And so you will recalculate your mu, you will recalculate your power allocation for those n minus 1 modes. If one of them is negative, you set it to 0 and you continue. And you do this till you have allocated power to all of them, until none of those power actually are negative, right? And so what will happen is effectively the following one. Here you have your mu is fixed to a certain level, and if 1 over rho is larger than mu, it means actually your power you will allocate to this here is negative. So in other words, you have to set it to 0. So here your power will be equal to 0, here will be equal to 0, and so on, till you have a certain number of power levels where they are either 0 or they are positive, right? And so this is how you can allocate your power to those different modes. Right? The strongest the eigenvalues, the strongest the power you allocate to them. Good. So let's see this over an example here. So imagine that. So let me add one more thing here. So I was saying that if rho is small, you allocate your power only to one of them, right? As rho increases, you allocate power to multiple eigenmodes, right? So how can this be interpreted in terms of mu? It can view this, if rho is increasing, you see that it means actually the bottom here of your ball is decreasing, if you like. The bottom is decreasing for all those eigenmodes, and so what will happen is that you will start allocating power to all those multiple eigenmodes, right? If rho is very large, it is very small. If rho is very small, this one will go up, this one will go up, and at some point you will have only one eigenmode, and you will allocate all your power to only one eigenmode, the strongest one. Okay? So the general behavior that you observe here is that if you have a very low SNR, you allocate power to only one eigenmode. If you have very high SNR, the bottom of your ball here will be very low, and so you will allocate power to more modes, right? So as you increase your SNR, essentially you will start allocating power to multiple streams, more and more, right? But always, you will always allocate more power to the strongest streams. Good. So here's an example where you have a matrix H, and the question is compute the capacity of this. And to compute the capacity, you have essentially to find what is the precoding matrix that you're going to use and what is the power allocation. So this is a good example of computing this water filling. And so you can do this at home in more detail, and you're going to have to do this because in one of the exercises in coursework 2, you're going to have to compute the solution of the water filling and the capacity of a MIMO channels. But you see here, you have a 2x4 matrix, right? 2x4 matrix means at most you have two singular values, and so you're going to have two eigenvalues of H Hermitian H, right? Two eigenvalues. You can actually compute those eigenvalues, and you can show that your eigenvalues are related to A squared and B squared. Now what you have a certain power level, you have a certain power here, and Pk is the power allocated to the K eigenmodes, so the K streams. So you see here, I'm not writing S1 and S2, I had before sum of Sk is equal to 1. That I mean that actually the fraction, so the fraction of the power allocated to stream K is given by S. Here, I'm writing the sum of the power is equal to P. So in other words, I'm not taking out my rho. If I write my expression of the SNR, I can write it two different ways. I can say log 2 1 plus rho Sk lambda K, right? And here I have Sk is a fraction of the total power, or I can say log 2 1 plus Pk lambda K divided by the noise power, right? My rho here is, let's say I call it Es over N. So Es here is my total power, or I can write it, if I use the same notation as what I have here, I can say it's P, right? So what I can write this is say either Sk refer to the fraction of the total power that I allocate to stream K, or I can simply write Pk is equal to the total power multiplied by Sk. And in that case, I'm looking at actually the actual power that is allocated to K. So this is actually two different ways of writing it. It's completely equivalent, obviously. But it just writes the optimization slightly differently, right? So in this problem here, and you will see this, in different books, and you just have to get used to it. It's very minor. But, oops, I didn't want to do that. I wanted to add here. So, right. So you could have either I try to maximize over Sk, and I have log 2, and I have a sum log 2 1 plus rho Sk lambda K, and I'm subject to Sk, sum of Sk is equal to 1. Or I can say it's a max over Pk of a sum of log 2 1 plus Pk lambda K over sigma n squared. And now I have a sum of Pk is equal to P, right? Is equivalent In this case, your solution will be a mu minus 1 rho lambda k plus, that's your sk. In this case here, your pk will be a mu minus 1 over lambda k divided by the noise power, right? In other words, I can say it's a mu minus rho divided by lambda k, right? You see, it's always related to the inverse of this term here. The inverse that actually is attached to sk is 1 over rho k, so it's 1 over this. Okay, it's exactly the same. It's just that in this case you're looking at the fraction of the power. In this case you're actually looking at the actual power. Okay, now in this example here, I'm actually looking at the actual power, so I'm looking at the pk, and so that's why I have p1 divided by the noise and p2 divided by the noise. Okay, you will get used to that. Now, what is my power allocation is mu minus the inverse of this and mu minus the inverse of that, right? And now I have to find my power level mu. How do I do that? I find mu such that I satisfy this power constraint. And so you can do this. Right? So you can do this, and you can say, again, as same as we did before, assume this term is positive, assume this term is positive. If you sum those two together, right, such that you obtain that, what you end up is mu is equal to that. And so if then you have a value for mu, you plug this value of mu into this and there, and you check whether actually they're both positive. If one of them is negative, you set the power to the weakest one to 0, and you put all the power to the strongest one. This is what you do here. You put the power to 0, and you put all the power to the strongest one. This is if this quantity is negative. So in that case, you transmit only along one eigenmode. If, on the other hand, by plugging this into this expression, if both of them are positive, right? If the argument here is positive and here is positive, it means actually you can allocate power to both eigenvalues. And so in that case, you're going to have a P1 and a P2 that are non-zero, and you're going to transmit over two modes, and each mode is going to have a certain rate. Okay, so go into more details. You know, into this example, try to solve it, and if you can solve this, then it will be very easy for you to solve one of the exercises in coursework 3. Good. So again, what's the main message here is that if you increase the eigenvalues of my channel matrix here, if I have one eigenvalue is larger than the other one, I allocate more power to the strongest eigenvalues. If my SNR is increasing, is large, I will have a tendency to allocate power to multiple eigenvalues. If my SNR is very low, I will allocate power to only one eigenvalue, right? So you will evolve by changing the power, this P1 and P2, essentially, or S1 and S2, you will evolve between dominant eigenmode transmission and multiple eigenmode transmission, but you will allocate your power optimally in order to achieve the capacity using this Waterfilling algorithm. Good. So this is summarized here. Low SNR and high SNR. At low SNR, I only care about the dominant eigenmode. I allocate all your power to the dominant mode. So I transmit only one streams. And so the rate of that stream essentially will be log 2 1 plus rho lambda max, where lambda max is the largest eigenvalues that I have. So if I have lambda 1 is larger than lambda 2, lambda 3, and so on, my lambda max will be lambda 1, essentially. Okay. If I'm at high SNR, I was saying earlier on, if I'm at very high SNRs, my rho is really huge, right? I have a lot of power. So if my rho is very huge, it means that here, in my example, my bottom here will be very low. This will go down, this will go down, this will go down, all will go down, this will go down. And so I'm going to have power that I can allocate to all those eigenmodes. So in the limit where rho goes to infinity, right, essentially the bottom level will be here, and I will be able to allocate power to all of them, right? So I will have, in the limit when rho is really extremely large, I will have actually a uniform power allocation among all those eigenmodes, right? So as a function of rho, at low SNR, right, if rho is equal to 0, for instance, you will allocate power to only one eigenmode, right, only one. As rho increase, at some point you will allocate power to a second eigenmode, so two eigenmodes. As rho increase, at some point you will allocate to all eigenmodes, right? And as rho is really large, you will allocate to all eigenmodes, but with uniform power allocation. So Sk will be 1 over n. Will be 1 over n. So I will have uniform power allocation in the limit of extremely large n. Okay? So you see that as rho increases, essentially you decrease the disparity in terms of power allocation. At small rho, you have large disparity of power allocation. You allocate power to only one of them, you put all the power and you put 0 to the other one. As rho increases, you start decreasing the disparity. And as rho gets infinity, you actually allocate power uniformly. That's what it means. Good, so that's why you have those two extremes here. Rho is equal to 0, rho is very large. And here what I'm doing, I'm having Sk is equal to 1 over n. I'm doing a uniform power allocation, so I have essentially rho over n. And I have n eigenmodes now. I have n data streams. I allocate the same power level to n of them, so I have equal power allocation. And this works well if I have really high SNR, right? At finite SNR, and this is what we mentioned already earlier on last lecture, if you do this at finite SNR and you allocate your power uniformly, it may not be a good strategy, right? If your SNR is very low, obviously doing this will be better than doing a uniform power allocation, right? We have seen this already before. But if your SNR is very large, right, you actually will end up allocating power uniformly across all eigenvalues, right, in the limit of really high SNR. Right? Now, if you have very large SNR, this term here is dominant compared to 1, so you can eliminate 1. And you will end up with two terms. You can break the log into log of rho over n and the log of lambda k. And so what you see here is indeed you're going to have n eigenmodes. And so your pre-log factor of the rate will be n at the highest SNR. In other words, your multiplexing gain will be equal to n. You will be able to transmit n interference-free streams in these systems. Okay? So for any channel realization, your capacity of that channel is always larger than allocating the power to the dominant, so that's the dominant eigenmode transmission, or using a uniform power allocation, right? In the very low power regime, this you're going to have an equality here. In the very high power regime, you're going to have an equality here. But in general, for any other regime, you're going to have an inequality, right? So your water filling solution here is always will give you a capacity or rate that is actually always larger than those two lower bounds. But in some extreme scenarios, it can boil down to those two lower bounds. Okay. Again, feel free to interrupt me, right, if you have any questions. Okay, so what does that mean in terms of architecture? What does that concretely mean? It's been the following one. Let me take this my 2x2 example again. I have my channel matrix H, I have my receiver, I have my transmitter. Right, and so what I do, I precode with VH, I combine here with UH. By doing that, I convert this into an effective channels where I have a lambda 1, a lambda 2, two eigenmodes. And I transmit two streams, C1 and C2. I transmit C1 here and C2 there, right? And I allocate power to C1, allocate power to C2 using the water filling solution. And so if lambda 1 is larger than lambda 2, I will allocate more power to C1 and less power to C2. What is the rate actually at which I transmit C1? What is the rate at which I transmit C2? The rate of 1 will be logged to 1 plus rho S1 lambda 1. The rate of stream 2 will be logged to 1 plus rho S2 lambda 2. Right? So I transmit n independent streams. They are Gaussian, so actually you imagine you have an ideal code where you have Gaussian inputs and you allocate a certain rate that is equal to that for stream 1 and that for stream 2. And so the total rate of your transmission will be the sum of R1 plus R2. Okay, where S1 here is S1 star, so it's the one coming from the water filling solution. This is the best thing you can do. You cannot do anything better than that, right? Now, in reality, if you take a 5G system, for instance, things are not that ideal, because first you have practical codes that are not infinitely long. You don't have Gaussian codes in the sense that you use finite constellation. So you will use QPSK 8 QAM, 16 QAM, 64 QAM, 256 QAM, and so on. And you will use a power allocation that will not be the water filling solution, but that will be something that actually try to quantize the water filling solution, right? So we will not get exactly the same rate, the capacity, but you could get relatively close to it, right? But the idea is the same in 5G. What you will do, you will transmit multiple streams and you will allocate, a different power level to those different streams as a function of your SNR, as a function of rho, and as a function of lambda 1 and lambda 2. Right? This is what is done in 4G and in 5G for single user transmission. Right? And you will simulate that extensively in course 43. Right. Good. Let me have a short break here, right? Just a few minutes. We can resume maybe at 10 a.m. And in the meantime, if you have any questions, yeah, feel free to let me know. There might be. Right, Xiaolin is saying more power is allocated to larger lambda. Yes, that's right. Right, so if you have different lambda, you allocate more power to the largest one. Okay, so have a drink or something, get some water, and then if you have any question, yeah, feel free to interrupt me.
Hello, Professor Bruno.
Yes.
Can I ask a quick question about the power location? And I mean, does this power location is performed by using the precoder at the transmitter side? The power location.
So the precoder here, right? So let's say, wait, I have this example. So here you have the precoder. It depends on how you define precoder essentially. So here, if your precoder is just VH, remember VH, this is actually has a unitary property. So this is made of multiple columns, right? Right. So I have VH is, let's say, V1 and V2.
Yes.
Right. So when I write VH multiplied by C, this means it's actually a V1C1 plus V2C2. Right. Now V, if they come from the singular value decomposition, the norm of V1 is equal to 1. And the norm of V2 is equal to 1. Right? They're already normalized there, right? So the power location is actually the power of C1 and C2, right? Okay. So what you could view, you could say the following. Let me take another page. So you could say what effectively you have is I transmit V1C1 plus V2C2, where this has a certain power, and I will allocate, let's say I have a power P1 and then a power P2, right? And P1 plus P2 is equal to my transmit power, right? Or what I could do is something different. I could say C1, A has a unit power, a unit energy, and C2 has also unit energy, but now I would have V2 and V1. I will scale V1 such that the norm of V1 is equal to P1 and the norm of V2 is equal to P2. If you see what I mean.
Okay, so actually it depends on how we treat the C1 and V1.
Yes, you can do whatever. Mathematically is always the same thing. What that means here is that this gives you the direction, and here you take your information and you scale the power of that symbol according to the power that you allocated, right?
Yes.
But you could have an alternative way that says, I always maintain an average unit energy for C1 and C2, but now I scale the power, scale the norm of V1. So the V1 is not only the direction, it also includes the power that is allocated there.
Okay.
So those two are fully equivalent. Mathematically, they're exactly the same thing. And you can use both, right? Yes. You just have to know what.
Okay, so in the reality, we usually give the power in the I think it's in the modulation steps. When we do like the QPSK modulation, we give the power. So maybe the power is first allocated to the C1 and the C2, and then V1 and V2 just the direction.
V1 and V2 direction. I mean, in the real system, practical implementation, in a practical implementation, I'm not sure, because you see what's happening is essentially, I can write this the following way. I could say this one here. I could say actually I have V1, the direction, multiplied by the square root of P1, multiplied by a unit symbol energy, right?
Okay.
So this one here, you could view this now will be a symbol with energy P1 or power P1, or you could view this one as now I have a vector, but the norm is not equal to 1, the norm is equal to P1, right? Depends on where you put it, right? Now, in reality, how you transmit this, you're going to have a C1, and you can view this as is precoded by something, right? Is precoded by something. And so this precoding here is essentially the entries of that. And then it goes to the antennas, right? Each of those antennas, right? And so as part of this, you actually have the power amplifier and all those things. So this is actually, you know, a baseband representation, but it's completely equivalent whether you want to allocate the power to C1 or you want to reflect into V1. Is really up to you. If you look at research papers, often we actually we write this in here. We put the power and the direction into one vector, and the reason for this is that we optimize the direction and the power jointly. Okay, so
okay.
Here in this MIMO case, point to point, you can split, if you like, you can split the direction and the power allocation. You can first do the directions, and then once you have the directions, you can decouple the MIMO channels, and then you can do the power allocation, right?
Okay. Okay.
But you could do them jointly, and so in research paper, if you read the research paper, you may see that if you take the research paper on rate splitting, we do optimization of the precoders, and the precoders includes the directions and the power allocation.
Okay, that makes sense. Thank you.
Okay, so any other questions, feel free to interrupt me. Right, so let's continue. So now let's move on to the case where we have fading channels, fast fading. So remember, this is something we did already before. We looked at the SISO case where we had fast fading channels, and we said two things. If you know the channels at the transmitter, then you can adjust, right, to each channel state. Or if you don't know it at the transmitter, what you can do is that you can encode over many realization of that channel, and you can transmit at an ergodic rate, right? And so here's the same thing. You can have perfect knowledge of the transmitter, right? And if you have perfect knowledge of the transmitter, it's the same as having a deterministic channel in the sense that for each channel realization, you do the SVD, you transmit along the right singular vector, then you actually choose your power allocation according to the Waterfilling, and you allocate your power accordingly. And then once your channel changes, you change your precoder, you change your power allocation, and so on, right? Your rate on average will be your ergodic rate, will be the average of the rate over each channel realization. But you could have also no channel knowledge of the transmitter or partial channel knowledge of the transmitter. For instance, you know the distribution of your channel gain, but you don't know exactly which channel realization you have. And so in that case, you can define an ergodic rate or ergodic capacity. So let's go over that. So let's imagine that I don't know the channels at the transmitter. So H is not known, but I may know the statistics of H. So if H is not known, I cannot change Q, the input covariance matrix, for each channel realization because I don't know it, right? So what is the rate that will flow in at instant K if I transmit with an input covariance matrix Q will be this log2 det 1 plus HQH, right? I transmit, I cannot adapt Q, so I fix Q, and then the amount of rate that can be transmitted over a given channel HK will be given by this. Now this quantity will fluctuate, obviously, because HK is not constant anymore, right? Is fading, and so on average, my average rate, if I can encode, if I have many realization much larger than the current time, will be a kind of sample mean of this rate of information flow that I had over each realization. And so in the limit where t is very large, what you end up with is you end up with the ergodic rate, which is the expectation of this quantity, where the expectation is taken over the distribution of h, right? So this is the same as what we had before when we were talking about SISO. It's the same idea. If you have one transmit, one receive antenna, you will actually end up with what we had earlier on in the first part of the module. But there is an additional bit here. It's not that your ergodic capacity will be given by the maximization of this quantity, where the maximization is taken over all possible input covariance matrices. They have to be such that the eigenvalues are positive. This is what it means by here being positive, and the trace has to be equal to 1 to maintain the power constraints. Right? Now, the one that maximizes this will depend on the statistics or the properties of H, the distribution of H. So for instance, if I have H that has correlated inputs, so let's say is circularly symmetric complex Gaussian inputs, complex Gaussian random variables, but there is some correlation between entries of H, then the Q will be a function of those correlation, right? But this is something that can be done. You can find the Q that maximizes this once you know the distribution of H under some assumption. What we'll do is that we're going to assume that we have IID fading. So I will simply assume that H is not IID distributed, right? So I have circularly symmetric complex Gaussian random variable, but on top of this, they're completely independent from each other. They're all identical and completely independent from each other. So physically speaking, what that means is that if I do that, it means that I have a large spacing. The spacing is very large. Remember, when we looked at the modeling of the MIMO channels, that means that the spacing is very large compared to the wavelength. And I have a large angle spread. The angle spread is very large, right? Or I have a lot of scatterers. That's what it means, right? So in that case, H are IID distributed, and the Q that maximizes this is given by a scale identity matrix. Okay, so what that means physically speaking, if Q is an identity matrix and actually is identity divided by NT, so the divided by NT means that you uniform allocate power across NT antennas. And that's because you don't know anything about your channel, and you just know that actually is IID. So IID means you have a lot of scatterers all around you. So what you do is that you just use an identity matrix and you divide your power uniformly across all antennas. You don't favor any particular direction. You don't do any form of beamforming in a particular directions. You don't allocate more power to a particular directions. You actually isotropically transmit power all around you. And the reason for that is because you don't know the channel, first thing, but second thing, you have a lot of scatterers all around you. So you have an IID behavior. And so that's why you don't favor one direction over another direction. That's the insight. If you didn't have the IID assumption here, if you had spatial correlation, and so for instance, if we had H was something like this, RR, HW, RT, right? You remember the Kronecker product we have seen before. If you had something like this, then the Q that you would choose would be a function of those correlation matrices, typically of the transmit correlation matrix, right? And in that case, what you would do, you would design the Q according to RT, and so according to the eigenvectors of the correlation matrix and according to the eigenvalues of this correlation matrix. Right? But here, if you're interested, this is in the book as well, how you can do that. But here we will assume you have just IID. So if you have IID, what that means that your Q is just a scale identity matrix and you allocate power uniformly across all those NT antennas. And again, so that means actually we have a log det. This can be written again as a sum of 1 plus rho. So if you want to do this again, just to make sure you're familiar, this is a very common manipulation when you play with MIMO. Right, so if you log 2 det I and R plus rho over NT H omega, and here I have the omega just to refer to the fact that that is really IID distributed, right? So if you have this, you can take SVD decomposition of this. So you're going to have a U sigma V VH right? Sigma u h v. So this will be identity matrix. This rho square will be the lambda, right? And I'm gonna have a log 2 that I and r rho over nt of u lambda uh, right? This is again log 2 that I identity matrix over this of lambda, right? You can always change the order here. And so this is 1 plus rho over nt multiplied by lambda 1 all the way to 1 plus rho nt multiplied by lambda k, right? And you have a log, so you're going to have a log 2 that's going to be a sum of log 2 1 plus rho over nt multiplied by lambda k, right? And so this is what we have here, essentially, right? And you have n of them, right? You have n non-zero eigenvalues. Okay, go from 1 to n. Okay. So what you see here is that this expression is slightly different from what we had earlier on. When we were doing the power allocation, the water filling, we had we had this, right? The sk, we could choose sk. No, I don't choose sk. I have sk is given by 1 over nt, right? So if you can optimize sk as a function of lambda k, you're going to have a higher rate. But for that, you need to know your channel at the transmitter. If you don't know it, you don't know what to do. And so that's why you end up with the sk now is 1 over nt, right? And your ergodic rate is given by the expectation of this. So you will encode over many realization of the channel. And if you encode over many realization of the channels, your total rate at which you can transmit will be given by this ergodic rate, ergodic capacity. Okay, so you can look at what happens at different SNR. Now, if you have a low SNR, you can show that this will be a function of just the Frobenius norm of the channel. So let me write this a bit further. So if you sum of this, and I expand this a bit, so I can view this slightly differently. This, I could say this is a log 2, a product, okay, from 1 to n of 1 plus rho nt lambda k. Okay, so let me take 2 eigenvalues for simplicity. So n is equal to 2. So I have a log 2, 1 plus rho over nt lambda 1, 1 plus rho over nt lambda 2. Right, it has a log 2. And now I distribute. I have a 1 plus rho over nt lambda 1 plus lambda 2 plus rho over nt square lambda 1 multiplied by lambda 2. Okay, so if rho is small, small here, it means actually this term will be actually probably more important than that term. So I could approximate as log 2 1 plus rho over nt lambda 1 plus lambda 2. That's what it says, right? And this is where it comes from here. If you have a low SNR, you're actually going to have just this term here. And what is this term? This is the lambda 2 plus lambda 1. You can show that actually the sum of the eigenvalues is equal to the Frobenius norm of the channel. Okay, so that's a property. So the Frobenius norm of h squared is, you can show that this is the trace of h multiplied by h remission. And the trace of this is going to be here, the sum of the eigenvalues. Right, so if I have 2, is the same. Okay, so you have this in the summary of the, you know, relationship, matrix relationship that I mentioned earlier on. You have this kind of relationship that is mentioned. Okay, so the sum of the eigenvalues will be actually is the Frobenius norm of H. So what that means is that means simply that if your SNR is low, your capacity here is mainly dominated by the amount of energy that you have in the channel, so the norm of that channel, right? If you had the higher SNR here, you see if rho is very large, this term now will become dominant compared to this one, and you will be mainly a function of the product of the eigenvalues here. Product of the eigenvalues means it's more related to the determinant of the channel matrix H, right? Assuming they're non-zero, right? So low SNR is more a function of the energy, so the Frobenius norm, and you're going to see high SNR is a function more of the product of the eigenvalues. And this is what you see here. The sum of the log is essentially the log of the product of the eigenvalues, right? So at high SNR, I'm going to have this n will appear again in front of the log, because simply I have n non-zero eigenvalues in this channel. My rate actually will scale with n. So that's the same if I have knowledge of the channel, the transmitter, or I don't have it. At high SNR, I will have a rate that will still scale with n. So I will still have a multiplexing gain of n. But the difference is that when I had the power allocation, when I had the water filling solution, I didn't have the 1 over nt. While now I have 1 over nt because I don't know the channel of the transmitter. So my multiplexing gain remains the same, whether I have channel knowledge or I don't have channel knowledge, but the power allocation is different. And so because I have 1 over nt here, I'm going to have some loss in terms of rates compared to the case where actually I knew the channels of the transmitter, right? But the multiplexing gain will be the same. So if you compare the rate that you have here with only knowledge of the distribution of the channel of the transmitter and the rate that we had earlier on with the water filling, when we solve this this water filling solution, so the optimal rate that we had here, right, given by that, and you do this over many realization of the channel, essentially you will see you will have a gap. Depending on the antenna configuration, depending on the number of receive antenna and the number of transmit antenna, you will have a gap, and that's because the power allocation is different. The multiplexing gain is the same, so the slope will remain the same. Right. Good. I will show you this in a minute. Now you can particularize this to the case where you have single antenna at one side of the link. This is something we did earlier on. So all those expression boils down to what we had earlier on in part 1. So let me show you that. Let's imagine I have IID channel, and I'm looking at now my ergodic capacity on the left side, and I have here my SNR. So my SNR here is my rho, right? And I'm looking at CSIT and CDIT. So CSIT is when I know the channel of the transmitter, right? So I essentially, for each channel realization, I perform the water filling, and then I take an expectation over all realization of the channels, right? So this is with CSIT. CDIT, I don't know the channels of the transmitter, and so what I'm having is actually this equation here. I'm plotting this, right? So I'm computing this for each realization of the channel, and then I take an expectation over all realization of the channel, right? With the CSIT, I also have an expectation or average, but this is not the same here because here is replaced by the log2, the sum of the log2 1 plus rho sk lambda k, where the sk is every time is designed based on the water filling for that specific channel realization. Okay. Good. So what do we see? So let's start with let's do this one. So I have those two here, right? So those two is this one and this one, right? Two antennas at the transmitter, two antennas at the receiver. And you see those two they are the same at high SNR, but at low SNR there is a small gap, right? Why is this? I have a 2x2 MIMO channel. At high SNR, remember, if I have high SNR and I know CS, I know the channel, the transmitter, so I have CSIT, I do water filling, but at high SNR, I allocate power uniformly across the two data streams, right? This is actually the same as what we do with CDIT. With CDIT, we have this 1/NT, which is equal to 2, right? So in both cases here, if I know the channel, the transmitter, or if I don't know it, my ergodic capacity here at high SNR is the same. At low SNR is different because here, if I don't know the channel of the transmitter, I will still allocate power uniformly across the two antennas, while with CSIT, I will have a gain in terms of rate because I will transmit one stream, and that stream will be along the dominant eigenvalues of that channel, right? So that gap here is because I allocate all the power into a certain directions in terms of transmitting it isotropically. Good. Now, if you have 4x4, right here, oops. If you have 4x4, this one and this one, you are here, right? If you have 4x4, what that means? At very high SNR, you see at some point it will converge. It's the same. At low SNR, is the same thing. At low SNR, there is a gap because at very low SNR, here, what I do here with the CSIT, this one, the upper one, at very low SNR, I transmit only one eigenvalue. As the SNR increase at some point, I will transmit along two eigenvalues, maybe three eigenvalues at some point, and at the end, I will transmit at with four eigenvalues. And in the very large SNR regime, I will transmit to all four eigenvalues with uniform allocation, so that will actually end up with the same rate, the same capacity as the CDIT, where I only know the distribution of the transmitter. Good, and then you can do the 4x2 and the 2x4. So if I have 4 receive antenna 2 transmit, or if I have 2 receive and 4 transmit, and I still have CSIT, this is here. So this is in green, those two, they're here. Right, they should be here, those ones. They're all on top of each other. So you can show that if you have perfect CSIT, whether you have NR multiplied by NT, so you have a 4x2 or you have a 2x4, so you switch the number of antennas at the transmitter and the receiver, the capacity is the same. You can show that, and the reason for this is because if you have a matrix H that is a 4x2, or if you take that matrix and you transpose it, and you have HT that is a 2x4, those two still have the same singular values, right? So the rate will be the same. Good. Then we have the CDIT here. And you will see you have a loss between the CDIT and the CSIT. And the loss comes from the fact that in the CDIT here, you will always transmit as 1/n. You will optimize your power allocation, right? So that leads to a certain loss. And so, for instance, here, this one here is a 2x4. 2 receive antenna, 4 transmit antenna. So this one, I'm not sure you see it well, actually, the yellow. Let me take the blue one here. Okay, so please. Sorry, so here I have the CDIT. And what you see is that the CDIT, this is the dashed line, is a 2x4. This is a 2x4. And the CSIT with 2x4 is here. right? So there is a gap there, right? So why there is a gap is because in this case here, this one, I have a allocation that is 1/4, right? I have CDIT, so I have 4 transmit antennas. While here, effectively at high SNR, because I have only 2 non-zero eigenvalues, that means actually at very high SNR, my allocation will be only 1/2, right? So that gap here explains, is due to the fact that at high SNR, essentially the CSIT and CDIT have different power allocation strategy. And I can have 1/2 simply because here I know which are the 2 main directions, and I can allocate power uniformly across those 2. While here I have 4 transmit antennas and I don't know where to transmit, so I transmit isotropically. So this is a very important figure. You will have to you will play with that in your coursework too. You're going to have to reproduce that and explain what is the gap between all those different antenna configuration, where the gap comes from. This is very important, right? So you're going to have to go back to the equation, try to understand where all those gaps come from. Right, the last thing I want to say is the CDIT. If I take 4/2 versus 2/4, this is different, right? If I have 4/2, that means I have 2 transmit antennas, so there the allocation will be 1/2. If I have 2/4, I have 4 transmit antennas, I will be 1/4. So I will have a gap between those 2. So in the CSIT, 4/2, 2/4 is the same, leave the same capacity. In the CDIT, 4/2 and 2/4 does not lead to the same results. Right? The 4/2 leads to a higher result than 2/4 because in the 4/2 you actually allocate power. In both cases, your rate at high SNR will scale as 2 log SNR, but you will actually allocate power as 1/2 versus 1/4, and that will lead to a gap. Okay. Now the slope here, this is your multiplexing gain. So the slope here, you have a slope of 2 for all those curves. Here you have a slope of 4. And how do you measure this? Well, if your slope of 2, that means actually if you increase by 3 dB, if you increase by 3 dB, so you go from 17 to 20, you increase by 3 dB. So it means you multiply your SNR right by a factor of 2. That means that you have, if you increase by a factor of 2, your SNR, you have a log 2 plus log 2 rho. So you gain 1 bits per second per hertz. If I now have a multiplexing gain of GS here, I'm gonna have GS there and GS there. So if I multiply by 2, that means actually I have an increase in terms of capacity that should be equal to GS. Right, so if I go from 17 to 20, I increase by 3 dB. I go from here, which is roughly 9, to here, which is roughly 11. I gain 2 bits per second per hertz. I increase by 3 dB, I gain 2 bits per second per hertz. That means actually I have a multiplexing gain of 2. Right? Here, you see, I go from, I don't know, from here to there, roughly I increase by 3 dB, right? And I go from 16 to 20. So now I increase by 3 dB, I gain 4 bits per second per hertz. I have a multiplexing gain of 4. Okay? So that's your slope, right? You should be able to read this. Good. So here you have an example. I will not go into that, but you have an ergodic capacity over fast fading channels versus SNR. You have different curves. And what you can do is that you know that you have NT plus NR is equal to 8. But depending on how you allocate your antennas at the transmitter or the receiver, whether actually you have 4x4 systems or actually 6x2 or 7x1, your rate will change quite significantly. And so the question here is you have 5 curves, how you map those 5 curves to different antenna configurations. Right, so you can think about this. You have the solution here, and so what you can do is that you can measure the multiplexing gain for those different antenna configuration here, here, and there, and then think about what antenna configuration could lead to such multiplexing gain. And there could be multiple solutions, right? So this is what you have here. Good. So what does that mean in terms of coding architecture? It simply means that now I have, since I don't know the channels of the transmitter, if I know the channels of the transmitter, I just do the same as on deterministic channels, right? That's very clear. But if I don't know the channel of the transmitter and I have IID channels, what I have to do, I cannot do this decomposition. And then what I have, let's say I have 2 transmit antennas and I have 2 receive antennas. What I do is that I transmit a number of independent streams here, right? And what I will have at the receiver, I will allocate power uniformly, so 1/2, 1/2 to those 2 streams. And what I have at the receiver, I cannot decouple those 2 streams, so they will go through the MIMO channels. And what I do at the receiver, I use a joint decoding. So here I have a receiver that performs joint decoding, right? Joint decoding, for instance, is maximum likelihood decoding. We'll see how we do that later on. So if I had CSIT and I had, let me write this in green. If I had CSIT, I could do a precoding here, a combiner there, and I had this channel matrix, and that was converted into effectively transmitted C1 and receiving something and transmitting C2. They were not interfering with each other, so at the receiver, I could have simply a SISO maximum likelihood decoder. Right? Now, here I cannot do that because I cannot decouple those 2 streams. I don't know H. I cannot precode along a certain direction, combine another direction to decouple those 2 streams. So I transmit with uniform power allocation. I encode over many realization of the channels, and at the receiver, I perform joint decoding to try to separate those 2 streams. Right? Those two architecture will lead to the same multiplexing gain, but the rate you achieve with this one will be higher because you have knowledge of the channels of the transmitter, and so you can change the power allocation and the beamformer and so on, and that gives you a higher rate, as we have seen. Here, for instance, right? You have a higher rate at final SNR, or here you have a final higher gain also. Okay, so knowing the channel of the transmitter has 2 benefits. One is actually to increase the rate, but the second one is to simplify the transmitter and receiver architecture, right? So here, because you decouple those 2 streams completely, you simply use a single antenna maximum likelihood decoder. So the same as if you have a SISO system. While here, you cannot do that. You need to have a joint decoding at the receiver. You're going to get a vector of observation signals here. And from there, you're going to try to infer what was C1 and C2 transmitted. And to do this, you need to do joint decoding, joint maximum likelihood decoding. So that has a higher complexity, right? Good. So last stage is when you have slow fading. So we looked at deterministic, fast fading, now slow fading. You remember what happened in slow fading. Now in slow fading, the channel changes slowly. You don't have, if you know the channels of the transmitter, no issue. You can always adapt as a function of the channel. But if you don't know it, then you transmit at a fixed, let's say, target rate, then you can have a problem because sometimes your channels will not be able to support that rate, right? And we were saying before, when you had SISO, that we had reliable transmission if we had log2 1 plus rho h square was larger than the rate at which you transmit, right? Remember? Then the channel can support that rate. Now here we have MIMO, and so what happens is that you transmit with a certain covariance matrix, input covariance matrix, Q, that is fixed. You don't know the transmitter, so you cannot change Q H, and just hope that the rate that is supportable by this channel, which is this, is actually higher than the rate at which you transmit. And so if this is the case, you can have reliable transmission. If not, you end up with outage. Okay, so this is captured through this outage probability, which is, again, generalization of what we did earlier on. Same concept, same idea, but slightly different things. Now I have a minimum here. So I'm looking at the probability that the rate that is supportable by the channel is smaller than the rate at which and we minimize the outage, right? This is what it means. So this is a bit more complicated to calculate. This can be done also under some assumption about age. And this leads to the same diversity multiplexing trade-off as what we had earlier on in this module in part 1. Remember I said that if you have a SISO case, you have a trade-off between how fast you want to increase the rate and how reliable the system is, right? So here we have the same thing. We have a multiplexing gain and we have a diversity gain. And there is a trade-off between the multiplexing gain and the diversity. So by this. So we'll not go into all the details. You can find this in the book, but what I want to show you is this trade-off. So what that means is the following. In the SISO case, we had a trade-off that was given by this straight line. So this is your multiplexing gain. This is your diversity gain. If you transmit at, it goes from 0 to 1. If you transmit at a rate that scales roughly as GS log 2R, right? F plus a constant. If you transmit with GS equal to 0, you transmit at a constant rate, you achieve a diversity gain of 1. If your GS is very large, right? So you transmit at a rate that increases with the SNR, what happens is your diversity. In the MIMO case, we have NR receive antennas, NT transmit antennas. What is the maximum multiplexing gain I can achieve? It's given by the minimum between NT and NR. This is the number of non-zero eigenvalues I have. Multiplexing. What is the maximum diversity gain I can have? Is NT multiplied by NR, because in my channel matrix H, I have NR by NT coefficients, right? If you remember Alamuti schemes, for instance, NR antennas and 2 transmit antennas, 2 NR diversity gain. In general, if you have NT transmit antennas, you can get at most NT and R diversity gain, right? Now, what it says is that if you want to achieve a multiplexing gain of this, you can do that over slow fading channels, but at the cost of diversity gain. So you can increase your rate very fast, but if you do that, your outage probability will be flat. On the other hand, you can transmit at the multiplexing at a rate that is quite low, does not scale much with the SNR. So let's say a multiplexing gate that is much smaller. But if you do that, you can achieve a diversity that is much larger. You can have much higher rate. That translates in this. This is your outage probability. Oh, sorry, there seems to be some echo. Okay, it's resolved. So this is the outage probability versus SNR. And what I show here is how this outage probability behave as a function of the multiplexing gain. So if the multiplexing gain is low here, I'm going to have a large diversity gain. If I increase the multiplexing gain, you see, then the slope of the outage probability will decrease. And so I will decrease the diversity gain. So there is a trade-off. Either you go for high multiplexing gain and low diversity gain, or you go for low multiplexing gain and high diversity gain. Right? That's a fundamental trade-off in slow fading channels. Okay, so same idea as what we had in the size, but now it's applied to the MIMO. So what that means? What is the implication of this diversity multiplexing trade-off? It means that because you don't know age of the transmitter and the channel is slow fading, you don't have the ability to encode over many realizations of the channels. This is quite different from the fast fading case. So in order to achieve this diversity multiplexing trade-off, the best schemes, what they're going to have to do, they're going to have to encode across multiple all antennas. So if you transmit a symbol only from one antenna, right, you're going to have a higher, you're going to have a quite large outage, likely because that antenna could go into outage, right? If the channel gain is weak on that antenna, you may go into outage. And so what is needed to achieve this diversity multiplexing trade-off is something a bit like Alamuti. You need to be able to transmit your symbol over multiple antennas. So C1 was transmitted over antenna 1 and 2, C2 over antenna 1 and 2. But that's what it means here. You need to actually join and code across multiple subchannels. The drawback with Alamuti is that when you transmit C1, you repeat C1 over the next time instance. So actually you do some form of repetition coding, and that decreases the rate of your transmission. So Alamuti would be very good in actually achieving this point here, having a large diversity gain, but the multiplexing gain of actually Alamuti is quite limited, right? On the other hand, you have other codes that actually can evolve here, have a higher multiplexing gain, but would have a low diversity gain. And then you have codes that actually can evolve over this whole domain here and that can achieve that. We'll see this later on as well. We'll briefly mention that. And those are codes that actually can adjust their multiplexing gain and the diversity gain according to this fundamental trade-off. So in reality, if you take a system like 4G, you don't have codes that achieve all this. The codes that are used, the strategies that are used, are either to maximize the multiplexing gain or to maximize the diversity gain, but you don't have a code that actually achieve the whole trade-off. And the reason for this is because those codes are more complex to implement as well. Okay. In 5G, the design is slightly different, and the emphasis is more on this side and less on this side. Right. So I will talk about this later on as well. Right, so what we're going to do now is to start looking at transmission and reception strategies and go into a bit more detail of actually transmit those, how we can potentially achieve. We know already we have some strategy to achieve the capacity when we have perfect CSIT. But if we don't know the channel transmitters, we have the CDIT, so this channel distribution information transmitter. We know just the distribution. I mentioned before that you may need to transmit multiple independent data streams, uniform power allocation, and then you do joint maximum likelihood decoding. What does that mean? So this is what we're going to see in this part, and then we can actually relax the complexity of the receiver and look at different receiver architecture. And then we look at also what kind of code we could build, simple code, in order to try to potentially achieve this diversity multiplexing gain. I will not go into much detail of this, but I will give you a flavor of what's happening. Right, so I think maybe it's not worth to start a completely new part, but let me give you a flavor of what we're going to get here. So the architecture we're going to look at is the following. We're going to have, at the transmitter, we're going to have multiple transmit antennas, NT, and we're going to look at how the bits of information now are mapped into those NT antennas. And so I will take B bits, and typically the way it works when you have a MIMO transmission is that you take bits of information, then you do the following. First you do error correcting codes. You can do, for instance, convolutional codes or turbo codes or polar codes or LDPC codes, whatever, trellis codes. And so you actually encode those bits into some other bits such that actually you actually robust to some noise. And then you do time interleaving. So time interleaving is to also improve the properties or the abilities of the code to correct errors when you have noise. And then you do symbol mapping. So you have those encoded bits that are then mapped into symbols. So for instance, here you have bits of 1, 0, 0, 1, and so on. They're encoded, and then you map this into symbols depending on your constellation size. You have QPSK, 16 QAM, 64 QAM, and so on. Once you have those symbols, then you have those symbols and then mapped into a space-time grid, right? And one of them, you know it already, is the Alamuti, right? What is the space-time coding here is essentially mapping Q symbols into a code word C that spans T transmit antennas and T symbol duration. So if you were using Alamuti, you had maybe symbol C1, C2, and you map this into a 2x2 matrix that was C1, C2 minus C2 conjugate, C1 conjugate, right? So this is an example of a code of a space-time code, right? And so whenever you have different bits coming in, you have different symbols here chosen maybe from a QPSK constellation like this, right? C1 and C2 are chosen maybe from this one, and then you map this into this a certain code word and you transmit this, right? So it spans NT transmit antennas and T symbol duration, right? But you could have other architecture, other encoding strategy here for your space-time code, right? You could have something where actually you transmit C1, C2, and then the next time instance, instead of repeating this here and there, you transmit another one, C3, C4, right? In that case, you see that here you have 2 symbol duration, but you transmit 4 symbols. Here you have 2 symbol duration, but you transmit only 2 symbols, right? Or you could have something else. You could have a function of C1, C2, C3, C4, such that part of the energy of C1 is transmitted on this antenna at this time, and part of the energy of C1 is transmitted maybe on another antenna at another time instance, right? So this is actually would be a mapping between the Q symbols and spreading that energy of those Q symbols in space and in time, right? So this refers here to time, right? And this would refer to space, right? So this is called space-time coding. You map your energy of your symbols into space and time, right? Instead of time, you could have frequency as well. So you could do space frequency coding. So you at a given time instant, you map over different frequency components. And then you could do space-time frequency coding where you map over 3 dimensions, right? The other thing you could do is, instead of having this block and this block separated, you could do them jointly. And so there are codes that do that. And some of the first codes that were designed for MIMO were actually doing this jointly. That's what's called space-time trellis code. So you have an error correcting code based on trellis, and you have a space-time code, and those two are designed jointly. So we'll not go into this. Those codes are actually not used in practice. They're actually very useful to understand how to design the MIMO transmission strategies. Unfortunately, they're not used really in practice because the most popular structure is really this. You have temporal coding like this, and then you have the symbols, and then you map into some space-time code. Now, what is important here is to understand that if you have B bits of input and you have T symbol duration, the ratio B over T is your signaling rate. So if you increase that, it means that per unit of time, you transmit more bits of information, right? Now, we're going to define also, I'm going to look at the spatial multiplexing rate, which is not exactly the same as the multiplexing gain, is the number of symbol Q that now you map in T symbol duration. So it means how many symbol Q you're going to map in code C. For instance, Alamuti here, Q is equal to 2, T is equal to 2. So Q over T is equal to 1. This example here, I have Q is equal to 4, T is equal to 2, so Q over T is equal to 2. So my spatial multiplexing rate here is twice as large as what I have with Alamuti. So I can transmit more symbols into limited time duration, right? So this can be interesting. On the other hand, you may have some loss in terms of diversity gain here because you see C1 is only transmitted from one antenna, not from the other antennas. While here, C1 is transmitted from antenna 1, but also from antenna 2, right? There is this trade-off that between rate and between diversity gain that will come up. Okay, so let me stop here. And what we're going to do next week, and be careful, next week means on Monday. So next week, we're going to have actually 4 hours of lecture, 1 lecture on Monday at 2 p.m. and 1 on Thursday at 9 a.m. And we're going to go into this into much. Right, thank you for your time. As usual, any questions, feel free to ask us. Don't stay in the dark, and I see you next week. Don't forget to submit your coursework by Sunday night, and otherwise have a nice day. Thank you. Bye-bye.
Thank you, Professor.
Thank you.